Hello and welcome to this lecture on the classification, importance and function of chemical compounds. I'm Madam Nurliawati and I'll be guiding you through this fascinating topic. Throughout this session, we'll explore the fundamental principles of chemistry that underpin our everyday lives, from the air we breathe to the materials we use. Let's dive into the world of chemical compounds and their diverse benefits. Let's begin by understanding the classification of matter. Matter is all around us. It's everything that occupies space and has mass. We classify matter into three main categories: elements, compounds, and mixtures. This classification is based on their composition and the way their particles are arranged. Throughout this section, we'll break down each category and learn what sets them apart. Now, let's focus on chemical substances. These are forms of matter with a constant chemical composition and characteristic properties. What makes them unique is that they cannot be separated into simpler substances without breaking chemical bonds. Chemical substances can exist as solids, liquids, gases, and even plasma. Examples include pure water, table salt, and oxygen gas. These substances form the foundation for everything in chemistry. Next, we'll dive deeper into the classification of matter, focusing on two key categories: elements and compounds. Elements are pure substances that consist of only one type of atom. On the other hand, compounds are formed when two or more elements chemically combine in fixed ratios. Both elements and compounds are crucial building blocks of matter and play unique roles in the world around us. Let's start with elements. An element is defined as a species of atoms that have the same number of protons in their atomic nuclei. While the number of protons is constant, the number of neutrons can vary, leading to isotopes of the same element. Currently, there are 180 known elements, with 94 occurring naturally and 24 being synthetic. Elements consist of only one kind of atom and they cannot be broken down into simpler substances. For example, oxygen is represented by the symbol O and aluminium by Al. These symbols, assigned by IUPAC, are standardized worldwide. Now, let's discuss the characteristics of elements. Each element is a pure substance composed of only one type of atom, such as copper in a wire. These atoms exhibit unique physical and chemical properties that define their identity. Elements cannot be broken down into simpler substances by chemical or physical means. Their classification is based on these intrinsic properties: metals, nonmetals, and metalloids, all of which play vital roles in the diversity of materials and phenomena we observe in the world around us. Elements exhibit unique properties. Take copper wire. It's a pure substance made of only copper atoms with distinct physical and chemical traits. These properties, like conductivity for metals or reactivity for nonmetals, help classify elements into groups. It's this diversity that makes them indispensable in both nature and technology. Let's explore the types of elements. These are broadly classified into metals, nonmetals, and metalloids. Metals are typically shiny, malleable, and excellent conductors of electricity and heat. Examples include gold, silver, and copper. Nonmetals, in contrast, are dull, brittle, and poor conductors, with many existing as gases at room temperature, like hydrogen and oxygen. Then we do have metalloids, the fascinating hybrids displaying characteristics of both metals and nonmetals, like silicon and germanium. The periodic table serves as a guide to locate and classify these elements based on their properties. The periodic table is more than just a chart. It's a roadmap to understand elements. Elements are arranged based on their atomic number, properties, and recurring patterns. Metals dominate the left and center. Nonmetals are on the right, and metalloids form a bridge between them. This organization helps classify elements efficiently, predicting their behavior and how they interact in chemical reactions. By studying an element position, we can infer its properties and its role in compounds and mixtures. Moving on to compounds, when two or more elements chemically bonded in a fixed ratio, we get compounds like water, H2O. Unlike elements, compounds combine to form entirely new substances with unique properties. For example, hydrogen and oxygen, gases at room temperature, form water, a liquid, when combined. This transformation underscores the beauty of chemistry. Compounds can be molecular or ionic. Molecular compounds like water or carbon dioxide are formed through covalent bonds where atoms share electrons. Salts, such as sodium chloride, are held together by ionic bonds where electrons are transferred. These bonding types dictate a compound's properties, making them vital in various applications. Not all combinations of substances are compounds. Mixtures like pizza or Kool-Aid consist of substances physically blended without chemical bonding. They can be homogeneous like salt water or heterogeneous where components like pepperoni or cheese are visible. Unlike compounds, mixtures retain the properties of their components and can be separated by physical means. Did you know mixtures can be separated without breaking chemical bonds? Techniques like distillation, filtration, or using magnets make this possible. These methods exploit differences in physical properties, such as boiling points or magnetism, to separate components efficiently. Mixtures can be solutions, colloids, or suspensions. Solutions are clear and uniform. Colloids scatter light but don't settle, and suspensions eventually separate. Visualizing these distinctions with a Venn diagram helps clarify their unique traits. Solutions are mixtures that appear uniform throughout, like sugar dissolved in water. Temperature often impacts solubility. Most substances dissolve better in hot water, but some, like gases, dissolve less as temperatures rise. Understanding solubility helps in everything from cooking to industrial processes. Chemicals play pivotal roles in our daily lives. From the foam in your mattress to the screen on your smartphone, chemicals transform raw materials into useful products. Through chemical reactions, compounds acquire properties ideal for specific applications like creating stronger plastics or more efficient fuels. Industrial chemicals are essential in manufacturing. For instance, catalysts speed up reactions in petrochemical industries. Pigments add color to paints, and surfactants stabilize cleaning products. These applications highlight how chemistry bridges science and innovation. Organic compounds, primarily made of carbon, fuel life's processes. From the DNA in our cells to the fuel in our vehicles, organic chemistry underpins biology and industrial alike, making it an indispensable branch of science. Inorganic compounds boast properties like high melting points and conductivity, making them ideal for uses like catalysts or coatings. Their unique characteristics drive advancements in medicine, fuel technology, and even art, with pigments in paints. In conclusion, the classification of matter, elements, compounds, and mixtures lays the foundation for understanding our world. Chemistry's applications are everywhere, from life-saving medicines to everyday conveniences, showcasing the importance of scientific exploration. As we wrap up, remember, chemistry isn't just in labs, it's all around us. Embrace this knowledge, explore its possibilities, and perhaps contribute to innovations that shape the future. With that, I'll end the lecture with thank you.